In this video, I'm going to do some review for Exam 2 by going through some of the important equations and derivations that will be helpful for the second exam. This video is going to include stuff from chapters 5, 6, and 7 up to pure liquid fugacity. This isn't going to cover all of the important material, but it is going to show a few important tricks and equations that I think would be beneficial to know before going into the exam. The first thing that would be helpful to study from Chapter 5 would be the Thermodynamic Web, which is basically the relations between different thermodynamic properties and how to derive certain expressions from others. This comes from page 274 in the textbook, and I think it's really helpful to be familiar with it because it shows you the easiest way to get from one thermodynamic property to another, and this can be extremely helpful when doing derivations. Like, for example, if you were given an expression for delta P over delta S at constant V, and they asked you to derive it in terms of T over CV, this would show you the path that you need to take in order to get to that final answer. So this could be really helpful. Definitely don't have to memorize it, but being familiar with different derivations would be important to know. The next thing to know is how to use these selected real gas equations that's given on the equation sheet. This is the equation sheet that you'll have for the exam. So for these real gas equations, this CPM right here and CVM in these equations are not for an ideal gas. So this is CPM for a real gas. And say if you were given an exam problem that gave you the ideal CPM, you would have to convert this to a real gas. So you would have to do this using different equations. So these are the two equations that you would use to convert from a CV ideal or a CP ideal that was given in a problem statement to CP and CV for real gas. It's likely that on the exam, if you were given a problem like this, that this correction term on the right for the CV and the CP would probably go to 0, but you would still have to show that this would go to 0, because most of the times in the problems that we work with, the second derivative with respect to temperature or the second derivative of volume with respect to temperature is equal to 0, most of the problems that we do. So on the exam, if you got a problem like this, you would need to write down this equation and show that this second derivative goes to 0, which validates the assumption that the CV of ideal is equal to the CV real. So when calculating dH, du, or ds on the exam, just make sure to remember that you would have to prove that this CPM term would be the same for a real gas as an ideal, or if it isn't the case, then you would actually have to calculate the CV for a real gas. The next thing I'm going to go over is hypothetical processes and how to choose the hypothetical process that you use for a given problem. With this material, when there is a change from one state to another of a species, you're almost always going to have to use a hypothetical process to do the calculations of the thermodynamic properties that you're interested in. So I'm going to go over the 6 possible hypothetical process pathways that you would have to use for this exam. Before I show the 6 different hypothetical process pathways, probably the most important thing that you can remember if you're given a problem with a hypothetical process is if the equation of state you're given is pressure explicit, you're going to start to derive how to solve for different properties by having that U, H, or S is equal to a function of temperature and volume, whereas if you're given a volume explicit equation of state, you're going to start with U, H, or S is equal to a function of temperature and pressure. I'll explain it a little bit more and derive the 6 different hypothetical process pathways that'll hopefully make more sense of what this means. So what this really means is that when you're given a volume explicit equation of state, the axes that you draw your hypothetical process on are going to be temperature on the x-axis and pressure on the y-axis. So you're either going to have a 2-step path that looks like this or a 3-step path that looks like this. And which one you choose between the two is dependent on the thermodynamic property that you are trying to calculate. So if you're trying to calculate a change in enthalpy, you're going to use the two-step pathway. And what you're going to start off with is, just like up here, you're going to have that the enthalpy or molar enthalpy is equal to a function of temperature and pressure. From here, you would take the total differential of the equation. From here, you can plug in the different fundamental relations, so you can plug in what dH is in here, and for here, delta H over delta T at constant P is just equal to the constant pressure heat capacity. So finally, you get that dHm is equal to this equation right here, starting from that it is a function of temperature and pressure, applying the total differential, and then plugging in different fundamental relations. When we apply this equation to our two-step pathway that we have over here, this first change in entropy is at constant pressure. So this dP term right here is going to cancel out. The change in enthalpy of this step right here is just going to be equal to Cp real dt, and you're going to integrate that over the change in temperature. The second change in enthalpy is at constant temperature, so this term is going to cancel out. And the change in enthalpy of this increase, this second step right here, is going to be equal to this term right here. And you would integrate that over the change in pressure. So finally, if you needed to calculate the change in molar enthalpy of a process like this, you would use delta Hm1 plus delta Hm2, where delta Hm1 is equal to this, and delta Hm2 is equal to this. Now for a du calculation. So for a du calculation, you're going to use a three-step pathway. Just like before, you're going to say that um is equal to a function of temperature and pressure. Then you're going to take the total differential and plug in any fundamental relations to simplify the equations. Doing that, you get that this is the equation for dum. And you're going to apply that to the three-step calculation, where the first step, there's no change in temperature, so this is going to cancel out. The second step, we're at ideal conditions because the pressure is at approximately 0. And we have a change in temperature. So this is just going to be equal to CVM, and originally it was at real, but since we're at ideal conditions, this simplifies it, and we can use CVM ideal. And the third step, we're going from ideal pressure to final pressure at constant temperature, so it's just going to be equal to this term. Now I'm going to do the same thing for a ds calculation for a volume explicit equation of state, and I'm going to do the same procedure. You start with that s equals a function of temperature and pressure. You're going to take the total differential and then insert any fundamental property relations that you can to simplify the expression. So I'm not going to go through each step and explain it, but here is what you would do for a ds calculation. This is the final answer for how you would get the change in molar entropy for a hypothetical process given a volume explicit equation of state. So I circled the final answers. So this is what you would do for a change in entropy, change in internal energy, or a change in enthalpy for a volume explicit equation of state in the problem. This is everything for a volume explicit equation of state, and now I'm going to do the same for a pressure explicit equation of state. I'm not going to go through each step, but I'm basically going to summarize for the three changes for dH, a du, or a ds calculation like before. These are the final expressions for how to calculate a change in entropy, internal energy, or enthalpy for a hypothetical process. The next thing I'm going to talk about are the assumptions that are necessary to state to prove that the clausius-clapeyron equation is valid. So in the equation sheet, you're given the Clapeyron equation, but you're not given the clausius-clapeyron equation. So you would have to state the assumptions and then derive the actual clausius-clapeyron equation in order to use it on the exam. So starting from the Clapeyron equation, first you need to assume that the molar volume of the liquid phase is much smaller than the molar volume of the vapor phase. Then you need to assume that the vapor behaves ideally, so according to the ideal gas law. And the last thing is you need to assume that the heat of vaporization is not a function of temperature. And then when all those three things are true, then the clausius-clapeyron equation shown right here is valid. So on an exam, you would need to state these three assumptions in order to prove that the clausius-clapeyron equation is valid. Next, I'm going to go over the equations that are important for vapor fugacity. So if you're working with pure component vapor fugacity and you're giving a volume explicit equation of state, this is what you want to use to calculate the fugacity. If you're given a pressure explicit equation of state, this is the equation you're going to use. If it's a mixture of species in the vapor phase, and you're given a volume explicit equation of state, this is the equation that you'll use to calculate the mixture fugacity of a certain species. And given a pressure explicit equation of state, this is the equation you would use to calculate the fugacity in a mixture of species I. Next, I'm going to go through the Lewis fugacity rule and when it is okay to assume that the Lewis fugacity rule is valid. The Lewis fugacity rule says that the fugacity component of a component I in a vapor mixture is the same as the vapor fugacity coefficient for I in the pure species. So it is okay to assume that the Lewis fugacity rule is valid when the pressure is low or the temperature is high, or in other words, almost at ideal conditions. If component I is in large excess, so if the mixture is made up of mostly component I, and 3, if the mixture is made of chemically similar species. So if there was a mixture of, say, benzene and toluene, then it would be a good assumption to assume that the Lewis fugacity rule is valid. The last thing I'm going to go over is pure species liquid fugacity. This is the equation that you use to calculate pure species liquid fugacity. Typically, in the problems that we work with, either one or both of these two terms in the equation right here is going to simplify to 1. So the fugacity coefficient at saturation pressure, is going to be roughly equal to 1 if the vapor phase behaves ideally or if the saturation pressure is less than or equal to 1 bar. And this exponential term right here, it's called the Poynting correction term, is roughly equal to 1 if the pressure of the system is less than 100 bar. So this is usually canceled out and equal to 1 in most situations that we will be given in these problems. I hope you liked this video and that it helps you study for the exam. If you like this video, give it a thumbs up and subscribe, and we'll be posting weekly videos for Chemi 211 at Purdue University.